Okay, so in the last video we were discussing the properties, and I want to show you another method how we can differentiate the kinds of properties. So one was intrinsic and extrinsic, which was dependent on whether the property is dependent on the mass or not. So those properties which are dependent on mass, such as the volume, for instance, are going to be called as extrinsic, whereas those properties which are independent of the mass, that means whether you have, let's say, a tablespoon of the material, or whether you have a bucket, or maybe a swimming pool, the density of water will always remain 1 grams per milliliter. And so those kind of properties would be called as intrinsic properties. So whenever you have to compare, two different kind of materials, let's say one of them is an unknown, what you do is you measure up intrinsic properties such as density, and you compare it to intrinsic properties of known material, and if there is a match, you have a winner. Um, Another way that you can classify properties is physical properties and chemical properties. Physical properties are those which are like density, mass, touch, taste. They've got not much to do with the chemical reactions and the chemical makeup. And in order to study them, you really, while studying them, you're not going to change the chemical makeup of the sample. For example, if you consider melting point, let's say you take ice and you allow it to melt to give you water. Now, in the process, H2O, which was earlier in the solid form, is now going to become H2O in the liquid form. But if you really think about it, the chemical makeup of hydrogen with oxygen still remains intact. So what I'm trying to say here is, if I can write in freehand here, what I'm trying to say here is that oxygen is bonded to hydrogen on both the sides, whether it is a solid solid water, or in other words ice, or whether it is liquid. The bonding doesn't actually change, and as long as the bonding is retained, we are going to say that it is a physical property. Let's talk about chemical properties. Chemical properties are those that when you study, you are going to see a change in the chemical makeup. For example, if you consider burning or combustion of a fuel, essentially whatever is the hydrocarbon, let's say that's methane. Methane is CH4. Let's write that, CH4. CH4. And when it burns with oxygen, it's going to give you CO2 and H2O. Of course, you will need to balance the equation. I should have just used the text to write this, type this, rather than trying to write this. But anyway, realize that methane will burn in presence of oxygen. It will go through a combustion process to give you CO2 and H2O. Jeez, what's going on here? And in that process, the chemical makeup of methane is going to change because in case of methane, as you can see, there are 4 CH bonds, whereas when it goes through the combustion process, now the entire assembly of the carbon hydrogen bonds is going to break, and you're going to end up with a CO2 and H2O. In order to balance it out, you will need 2 moles of oxygen, and that's going to give you 2 moles of water. So realize things like rusting, for example, where iron becomes iron oxide, Fe2O3, or souring of milk, where there's lactic acid accumulation, and we of course have lactose as the sugar, or when you take a photograph. So essentially there's an oxidation reaction that goes on, and silver bromide is utilized in that case. Digestion of food, you have glucose or sucrose, which is going to, or starch for that matter, which is going to eventually break down into glucose and eventually generate energy and give you CO2 and water, which is then excreted from the system. All of these start with the starting material A and give you something else altogether. And whenever there is a change in the chemical makeup, we call it a chemical property. So you can say that any chemical reaction is really a chemical property. And so for that reason, one can say that a physical change will involve physical properties. So things like shape, color, odor, boiling point, density, these are all physical properties, whereas chemical change is a chemical process or a chemical reaction, and in that case the old substance is completely destroyed to make way for a new substance. So on that note, let's kind of recap a little bit based on what we know about mixtures and pure substances, compounds, elements, etc. The question here is, which of the following represents a mixture? So hopefully you can see that A has red and blue spheres, B has all red, and C has all one red, one blue. So hopefully you can see that it is A which has two different kinds of components, hence that represents a mixture. Just for the sake of argument, if you had to predict the nature of B, you would say that that's an element because it's all, both the spheres are red. And in case of C, since one is red, the other is blue, that means it's some kind of a compound. And all the units essentially show that. So this must be a pure substance, but pure substance of the format of a compound. Now, this was the qualitative behavior, and now in the next half of this chapter we are going to discuss the quantitative behavior as well. So there are two terms that I want to discuss. One is called as accuracy, the other is called as precision. If you think about it, what those are, accuracy is really pertinent to the true value of the given measurement, whereas precision is essentially how well the entire data follows one another. So for example, here if you look at the three figures, you can see that A, the data points kind of follow each other, but they haven't really hit the bullseye. So this first one is actually precise data. This is a precise data. Whereas when you think about B, it has hit bullseye as well as it is following each other. So this is accurate and precise. And the last one is pretty much random. Neither did it hit bullseye, nor did it, nor does it follow each other, and hence it's neither accurate nor precise. So in lab, when you're working, you obviously would want to have data which is accurate as well as precise. And depending on the kind of data that you generate, of course, points are allotted for both precision as well as accuracy. Now, the one thing that I want to mention here is a lot of times people have a tendency to interchange accuracy and precision, and that is not really correct. In order for you to be able to make claims about accuracy, you must know what the true value is. In order to make claim on precision, you must have more than one data set to be able to compare one to another. And hence, that is how accuracy and precision, that is how those two are connected or related. So, just to give you an example, let's say there is a student who makes a measurement. So let's call him student 1. He makes a measurement of 3.211 grams. All right. There is another student who makes another measurement, and that comes out to be 3.222 grams. There is a third student who makes up a measurement 3.215 grams. Okay, and the question is, what can be said about this data of the three students. Is it accurate? Is it precise? Is it both accurate and precise? Or none of the above? If you think about it, the three values do follow each other, but we have no idea what the true value is. So nothing can be said about the accuracy. But since the three values follow each other, they definitely are precise. So this data is just precise. Nothing can be said about the accuracy of this data. I hope that is clear to everybody. Let's then discuss scientific notation. You probably already know this from school, but scientific notation is a method where one can actually write data in a specific format, and that format is that you put up a number, let's put a hash for that, dot number, you know, however many, times 10 to the power of n, where n is some kind of an exponent. It can be a positive value and it can be a negative value. The reason why anybody would want to write scientific notation is for the ease of reading data. Imagine if you're measuring, if you're an astronomer or an astrophysicist, more importantly, and you want to, you're studying you discover some new planet and you want to make some predictions about what's going on there, and you're carrying out your studies there, and that involves distances which are like really gigantic, and this is to the tune of maybe 13579820000. I don't even remember what I said. It's a pretty big number. On the other hand, if I write it as a scientific notation, in a sense, it's going to give me a highlight of how big that number, a sense of how big that number is. On the other hand, if you're a person, a biologist who is in charge of making measurements of small organelles in a cell, and the numbers are really tiny, in that case, this number, this exponent, is going to have a negative value. So the part where I'm saying here large to small, when you're converting large to small, that just means 123,987, that's large, and then 1.23987 is small. So basically, in going from a very large number to represent that in a scientific notation, you will have to move it 5 places in this case on the left hand side. On the contrary, if it's a smaller number, then you will have to move it on the right hand side. So 0.000239, in order to write it as number dot number, that format, you're going to simply move it 1, 2, 3, 4 decimal places, and since you went in the right direction, we basically put in a negative sign in front of it. Okay? All right, the question is put into or take out of scientific notation. I'm just going to pick any two, and you really should work on the remaining in your own time. And if you have any questions, feel free to ask. Let's pick the first one. It's maybe I'll use the text again. It's 87542. If I were to put it in the scientific notation, the decimal right now is right after 2. So I'm going to move it 1, 2, 3, 4 spots. So it's going to be 8.7542 times 10 to the power of 4. Let's pick another one. Maybe let's remove it from the scientific notation. So now you have 2.1956 times 10 to the negative 3. So you write down 21956, and since it's a negative power, that means you want to put it 0, 0. You want to put 2 zeros before the 2, because that would mean that you have to move it 3 times on the left hand side. So realize 10 to the power of negative 3, that's a small number, whereas 10 to the power of 4, that's a larger number. Again, the reason why